All right, thank you for your patience, and we start now. Once more, thank you, and thank you for attending our technical seminar today. Today we have Mr. Antonio Ledesma from Parson Brickenhoff as our guest speaker. Antonio is a bridge engineer, and he actually has 12 years of experience in bridge engineering industry. He got his Bachelor of Science from the North Carolina State University in Civil Engineering, and then he graduated with his Master from the University of Texas, Austin in Structural Engineering. Since that time, he's been in the bridge industry, and now he's working with Parson Brickenhoff. Now he's located in Denver, Colorado office, and what he will be presenting today is two case studies that he was involved in the design of them. They were balanced cantilever segmental bridges. If I want to give you more detail about them, is that these two cases, one of them was I-95, intersection of I-95, I-295 in North Interchange project, which is located in north of the city of Jacksonville in Florida. And then I-4 and Leroy Selmon Expressway Interchange, which is located in Tampa, Florida. Both of the bridges are constructed using the balanced cantilever method of construction. Then the objective of today's presentation is for the audience is to gain and understand the design of the precast segmental bridges using balanced cantilever method. So I will turn it over to Tony, and we'll ask him to start the presentation. And if you guys have any question during the presentation, please feel free to send it using the question option, and we will be answering the question. If it's a general question, we'll be answering that, and if it's regarding the presentation, Tony will answer those at the end of the presentation. Thank you so much, and let me change the presenter, and Tony, you may start.
Okay, good afternoon, everybody. I hope you can hear me. Thank you for joining us and for this presentation of a basic design of balanced cantilever bridges. As Puya mentioned, I'll discuss two projects that I was a design engineer on, and hopefully you'll get a basic understanding of precast balanced cantilever design. So the presentation will discuss some learning objectives, basic balanced cantilever construction, and then I'll go into the two case studies. One is the I-4 Leroy Selmon connector in Tampa, and the I-95, I-295 North Interchange in Jacksonville, Florida. And then if anybody writes in a question, I'll attempt to answer them. So the learning objectives today would be just a basic overview of balanced cantilever construction, the balanced cantilever construction method. Some basic design considerations in determining the segment layout and span layout of the bridge, general discussion on the structural analysis of a precast segmental balanced cantilever bridge, and some detailing issues and protection measures for post-tensioning tendons used in Florida. So for a balanced cantilever construction, balanced cantilever, for those who aren't familiar with it, is, and this is precast balanced cantilever, is basically the construction method involved of progressively erecting segments on alternating sides of the pier segment. So you're erecting one segment on one side and then transferring to the other segment to the other side and erecting another segment, and progressively cantilevering the segments out on alternating sides. Successive balanced cantilever units are then joined together using a cast-in-place closure pour or stitch pour to form continuous units. The end spans, since are don't have a way of balancing on the other side, unless you can do so. There are some special considerations you can do, but generally those are erected and supported on fault work. So some advantages of balanced cantilever construction include the ability to construct over traffic, short lead time compared to acquiring steel and fabricating steel elements, the use of local labor and materials, whereas the precast segments are usually cast on site or very close by, and local materials and local labor are typically used for the construction or erect segment casting, as opposed to shipping in large steel girders or tubs. And balanced cantilever construction can be erected using trusses to eliminate ground-based, crane-based erection. So the first project I'll discuss is the I-4 Selmon Expressway interchange. I'll discuss one of the ramps, Ramp C, and go through the balanced cantilever construction sequence, and then talk about some unique features of this bridge. So the project is located in Tampa. The horizontal road on the top of the picture is Interstate 4 connecting Tampa to Orlando. The expressway along the bottom of the page is the Selmon Expressway. So the DOT has proposed to connect these two major thoroughfares with what they call the I-4 Selmon Expressway connector. This project was so large that they basically split it up into two different sections. The north section was designed by Parsons Brinkerhoff, and the south side of the project was designed by a couple of other firms. So for this project, due to the scale and to promote, to get the most aggressive bidding, 4 alternates were let for the project. Bid alternate 1 consisted of using all steel box girders. Alternate 2 consisted of an all segmental approach with a mix of balanced cantilever and span-by-span construction. Bid alternate 3 included steel girders for the flyovers, and the red section shown in the picture is called the viaduct. The viaduct would be constructed out of bulb T-beams, and the 4th alternative was using segmental bridges for the flyovers and bulb teeth for the viaduct. So the chosen bid package was a segmental with the Florida bulb teeth for the viaduct. So the bridge I'll be talking about today is that this is the north interchange with the connection to Interstate 4. So there's 2 balanced cantilever flyover ramps at this location. Oops. So some of the ramp statistics: this bridge was constructed using precast balanced cantilever construction method. The length of the bridge was 940 feet with a width of 45 foot 3 inches to accommodate two travel lanes and shoulders. 6 spans and comprised of 102 precast segments. The largest span was 180 feet, and the horizontal curvature of the bridge was approximately 600 feet. The bridge was completed in 2012, and the project overall should be completed roughly maybe summer of next year. So shown here is a typical section showing that the bridge carries 2 lanes of traffic, and the shoulders. As you can see, the depth of the girder is 9 feet. The top slab is 10 inches and the bottom slab is 9 inches. So the pier segments are, for this bridge, it's constant depth throughout. The height of the bridge was not increased near the piers, and this was to tie into to an existing project, the Selmon Expressway, and keep the box proportions similar. And the depth of the structure is 9 feet deep. The span to depth ratio is 20 for this bridge. The precast pier segments were comprised of 2 separate 5-foot length segments. This is typically done to reduce the lifting weight. However, the contractors always have the option of joining the two segments and lifting them onto the pier, as they've done here in this project, as you can see in the picture. The foundation is comprised of 36-inch drilled shafts. We try to use one typical size footing to increase efficiency and limit the number of foundation types. However, there was a special foundation at Pier C4, which we'll discuss in a little bit. So to erect the balance cantilever construction, we typically use temporary towers supported on the footing. These towers can be supported off the footing on their own foundations, but typically it's easier to support them on the footing if your footing is designed to accommodate the overturning moments on the temporary towers. If not, these towers can be spread out further and supported on temporary footings of their own. So shown here, what I would show you here is the basic construction sequence for a balance cantilever construction using the Midas software. So typically you would use a specialty software like Midas or others to simulate the stage construction of the bridge. Typical software packages don't allow you to actually have separate models or separate structures not joined together in the same model. So typically you need to have some kind of specialty software to allow unconnected structures and to take into account the time-dependent effects and loading history on the structure. So here we would typically start with erect the substructure, the columns, and then erect the pier segments. Successive precast segments are joined to the pier segment on alternating sides and connected using cantilever, what we call cantilever tendons in the top slab. So as you progress outwards, you install new cantilever tendons of varying lengths. So during this unbalanced phase, what I've shown is two segments erected, but typically you would erect one at a time, join them using temporary erection PT bars, and then join the other segment, and then connect those two segments with the entire structure using a cantilever tendon. So to handle the out-of-balance forces during erection, the temporary towers will be modeled as shown here, which can be modeled as a temporary support beam member, or you can be modeled as a spring. So this is what it would look like during actual construction. The temporary towers supporting the structure during cantilevering. The cantilever tendon is located in the top slab, and typically a work platform is installed at the end so that workers can access and stress the tendons during erection. This particular bridge, you can erect the segments numerous ways. The most common way is using ground-based cranes. But however, for this project, a segment loader was used to erect the segments. And the advantages of using a segment loader is if you have very tall piers or you're over a terrain where locating ground-based cranes isn't feasible, then the use of a segment loader is very beneficial in the sense that you can deliver the segments to the site near the piers in one location. The segment loader can drop down, pick it up, and move it out to the cantilever without which may not be possible using other construction methods. So shown here is another view of the segment loaders. As you can see on the left picture, the segments are brought to the site on a flatbed truck and lifted by the segment loader into position. The picture on the right shows shows the balance cantilever construction over roadway. So as you can see here, where the process will continue, where you erect segments on alternating sides, and you continue erecting until you finish the balance cantilever unit. So here you can see the finished balance cantilever unit for one pier segment, pier location. Right now, currently all the tendons are in the top slab. There will be some Erection PT bars in the top slab and the bottom slab. As segments are erected, you will have to apply an epoxy coating to join the two segments for durability, to prevent water from getting in the segments, and to make to join the two segments together more effectively. So after you finish erecting the first balance cantilever unit, the end segment to the abutment or maybe to another continuous unit is erected. These end span segments are typically erected on false work. So after the end spans are erected, the unit is made continuous by the use of bottom continuity tendons, which go through the bottom slab and provide positive moment capacity. And also, some states require the use of external drape tendons. Not all states do, but external tendons are also used. External tendons are required in Florida, and one of the benefits is that one, you get some redundancy. Two, due to the drape nature of the strands of the tendons, you get additional shear capacity, or it really helps your shear capacity near your supports. So here you can let me see. So here you can see a picture of basically two finished cantilever segments and the end span segments being erected on false work. The end span segments are typically supported on this false work of beams or possibly rails, and the use of jacks under each segment will be used to level the segments and make sure that they're aligned properly. So after these end span segments are joined together, a cast-in-place closure pour will be constructed between the end span segments and the cantilever segment to make them continuous before stressing the bottom continuity tendons and the draped external tendons. And typically also not shown in the previous diagram was that you would, across this closure pour, you would also install top continuity tendons to join the segments also. So shown here is an inside view of the box girder, showing you the external drape tendons and the bottom continuity tendons. After construction, or after stressing, the bottom continuity tendons are coated with an elastomeric coating to prevent any contaminants to get into the tendon and into the strands. So shown here is it would be an overall here would be an overall view of the construction of the balance cantilever bridge for the entire bridge, starting out with the erection of one cantilever unit joined by the end span. Then successive balance cantilever units are erected and joined to the previous one using at the cast-in-place closure pours. So this process is continued until you get to the end of the bridge and you erect the end span unit on that end. So one of the questions is typically, why do you need a, what's the difference between this method and a traditional method of, say, erecting a bridge on false work, and why you need specialty software to design these types of bridges. Some of the reason is, as you can see in the top photo, in the top picture, a typical bridge constructed on false work would give you this type of moment diagram due to the dead load. And this would just basically be a uniform load. It equates to a uniform load on a continuous structure. So the moments in the moment girder diagram will show you that you get large negative moments over the piers and large positive moments near midspan. However, when you erect a bridge using the balanced cantilever method, because the structure is, each balanced cantilever unit is isolated during erection, all of your moments are negative moments. So the only positive moments you get due to dead load is when you cast the closure pores. So your moment diagram is essentially shifted upwards, so you have very little positive moment and you'll have much higher negative moments as compared to if this bridge was erected on false work. And in addition to that, as a designer, you would also be very aware that the moments and the loads transferred to your substructure would be opposite of what you would expect if you erected a bridge on false work. So shown on the left is a bridge erected using the balanced cantilever method. So as you make a cantilever unit, as you can see in the left picture, the left graphic, the picture on the left shows you the deformed shape, and the picture to the right of that shows you the moment diagram in the column. So as you erect one cantilever unit, the centroid of the weight of the cantilever unit is towards the inside of the curve. So therefore your column wants to deflect in that direction, and you'll have moment. Your transverse moment in the column is as shown in the picture in the moment diagram on the right. The graphic on the right shows you the deflected shape and moment diagram if you were to erect this bridge on false work. So if you erect a continuous unit on false work, the centroid of the span is towards the outside of the curve. So your moments in your column would be towards the to the outside. And so, like, using the two different methods, your inside bearing, your outside bearing, maximized for dead load moment would be opposite. But as you join these structures and you make them continuous, and then any loads applied after that would be the same. So continuing this, for this bridge, Ramp C, there was a unique situation where we had one of the piers had to be designed to accommodate the future high-speed rail corridor. So the available width, the width of this corridor was only allowed only a 4-foot diameter, a 4-foot width opening for the columns. So to accommodate this, this pier was skewed, and basically we used two columns, 4 feet in width, and which ran down the middle of this corridor. So to accommodate the location of the bearings under this for this column, we couldn't use a typical pier segment. So in order to accommodate this, we basically split the two precast pier segments and installed a 5-foot width typical segment in between those two, and then came back and filled this precast segment with the cast-in-place concrete, so that essentially the typical segment acted as a form for the cast-in-place concrete. So this pier segment ended up being 17.5 feet in length, as opposed to the 10-foot length of a typical pier segment. So with the offset skewed bearing arrangement, we had to make sure that this pier segment would be could accommodate the loading And so we investigated the torsion in the Pier Segment. And so here you can see the shear flow, or the force vectors in the top slab, so that we could design our post-tensioning and the transverse post-tensioning in the top slab of this unit. So the next project I'll discuss is the I-95, I-295 project in Jacksonville, Florida. I'll discuss some design considerations, some unique features, and also discuss some of the Florida DOT requirements for segmental bridges regarding post-tensioning requirements and also tendon protection measures. So the bridge is located at the north interchange of I-95 and I-295. This flyover ramp is located approximately 1.5 miles south of the Jacksonville International Airport. The existing interchange is a partial cloverleaf. This interchange will be upgraded to an all-leg interchange in the future. So part of the first phasing of this upgrade is this ramp SE, which is the bridge we'll be talking about today. Ramp SE carries traffic from southbound I-95 to eastbound State Road 9A. So shown here is the all-leg interchange in the future. As said, this interchange would be constructed in multiple phases, 3 phases total, and will potentially be let sometime in the near future. So when designing this ramp, the future interchange needs to be considered, and so as part of that, the vertical profile of this ramp needs to be minimized in order to not affect the future ramps that will fly over this one, or to minimize the effect of the future ramps flying over this one. So shown here, ramp SC is the 3rd level ramp in this interchange upgrade. The ramp will fly over I-95, the 1st level I-95 southbound and the existing ramps, and the 2nd level being the I-295 State Road 9A level, and then ramp C's 3rd level. Future ramps will comprise the 4th level. So 2 main structure types were identified as the leading candidates for this bridge: steel box girders and segmental box girders. The segmental box girders were chosen based on the bridge type study and estimated construction cost. So the length of this bridge is a little over 2,200 feet, has a width of 49 feet 3 inches, is 10 spans, and is comprised of 234 segments. It's typically unique to have a segmental bridge, a precast segmental bridge, cost-effective with this many segments. Typically, precast segmental bridges are most cost-efficient when you have numerous precast segmental bridges where there is some economy in segment casting and segment fabrication, or as part of large projects or long spans where it would be more beneficial to have the precast segments. The largest span on this bridge was 274 feet, and the horizontal curve on this bridge was 1,250 feet. So typically span arrangement for these any type of ramp flyover is dictated by what's underneath, and this bridge is no different. Column locations are limited, and so sometimes it can be difficult to optimize a segment layout while accommodating efficiency and avoiding existing roads underneath. So if designing a precast segmental bridge, definitely repetition of span, repetition of segment layout, and segment lengths is crucial in order to have a cost-effective structure. So here you can see the 10 span unit and the number of roads that it has to cover or has to span. So shown here is the 10-span bridge modeled in Midas. But due to the span length of this bridge, 274 feet, the segments are variable depth. The segment depth varies from 9.5 feet at midspan to 12 feet at the piers. This 12-foot, the variable segment depth is varied over the 6 segments adjacent to the piers. So for the 274-foot span, the span to depth ratio is 23, and the end pier locations, piers 2 and 10, the structure depth was kept constant due to the smaller spans at the end spans. So the control expand to depth ratio for these 2 pier units was 24. So here, this bridge was erected using a ground-based crane. The contractor is able to place the crane close enough to the superstructure to accommodate erection of all of the segments. So the use of overhead gantry or segment loaders was not necessary for this bridge. So here you can see one of the precast cantilever segments being erected, and in the bottom picture, the end span unit on false work being erected prior to the closure. So the foundations for this bridge used 30-inch square prestressed piles, and out of the 10 piers, only 2 footing sizes were required. And as mentioned before, the footing sizes and foundation types are typically minimized to accommodate to increase efficiency and make it easier. The temporary towers were supported on the footings, so eliminated the need of special footings or separate independent foundations for the towers. So the typical segment for this structure was 9.5 feet. Temporary PT erection blisters in the top slab were used because the temporary PT because the erection PT bars were external. At the end of construction of one cantilever unit, the PT bars could be de-stressed and reused on the successive balanced cantilever units. And one of the benefits of using external PT bars is that since they will be taken off and reused, you don't have to grout them in place. If you locate your PT bars, erection PT bars, in the slabs and they remain permanent, you would have to grout those. So when possible, it can provide some type of savings and convenience to the contractor. In the bottom slab, a mix of external and internal PT bars were used. The external PT bars were used in the bottom slab near the pier cantilevers due to the varying depth. Oops. So due to the varying depth, there's a radial component to the PT bars as 2 PT bars connected in the segment create a radial force that could potentially lead to a spall in the bottom slab. So in order to mitigate this, these PT bars were external. As we got to the constant depth sections, the PT bars were made internal, where it did not would not potentially cause spalls. Another reason why typically bottom slab erection PT bars are internal is that you'll have, if they're external, they potentially interfere with the bottom slab continuity tendons. So in order to move them out of the way and not interfere with the deviators, external tendons, and the continuity tendon blisters. They're typically made internal. So here you can see the transition, how the transition was made between the external PT bars and the internal PT bars, and where the overlap, with an overlap, so that you get constant compression force in the bottom slab. So here is the 12-foot deep pier segment. These pier segments were also split pier segments, and also erected by the contractor on the ground and lifted into place. An additional benefit of splitting the pier segments is also for transportation issues. A narrow width segment, and also because the diaphragms are typically solid with an opening for the opening in the diaphragm for access. The segments are fairly heavy, so this also reduces the transportation weight. So shown here is a deviator segment. Deviator segments are used to accommodate the external post-tensioning tendons. Where necessary, the deviators can also accommodate the bottom slab blister. So with the full height deviators, what they do is direct. They align basically they align the external post-tensioning tendons and also future post-tensioning tendons in the slab or inside the box girder. And they also provide horizontal deviation, since this bridge is on a 90-degree curve. The deviators basically will enable keep the post-tensioning for enough away from the inside web to not create a conflict with the tendon hitting the inside web of the girder. So some Florida DOT minimum tendon requirements. Florida has their own unique tendon requirements for balanced cantilever or segmental bridges. These requirements are not used everywhere. Every state is different, but Florida DOT has some additional ones to enhance the redundancy of the bridges. So at mid-span closures, we're required to have 2 bottom slab tendons per web and 1 top slab continuity tendon per web. End-span units must have a minimum of 3 tendons per web, and they also must have 2 external webs per tendon, 2 externally draped tendons per web. So this redundancy, these measures are to promote tendon redundancy, structural redundancy, and provide protection, which are vital to long-term durability of the structure. There have been some very well-documented cases of tendon corrosion in Florida DOT bridges. So these measures are there and in place to ensure durable structures. So an additional Florida DOT requirement is to have tendon duct couplers. These couplers must be continuous through the segment joint, the precast segment joint. The old method of balanced cantilever construction or precast segment construction involved the use of maybe like a neoprene seal between the segments. However, that method, a lot of times during the grouting of one tendon, you would have some crossover or some grout leakage from one tendon going through a crack and penetrating another adjacent tendon duct and basically clogging up that tendon duct. So what these tendon duct couplers allow is basically an isolation, more isolation between the 2 tendons to form a continuous duct to prevent grout crossover to adjacent tendons. And these tendon duct couplers must be able to accommodate straight tendons and a skewed tendon alignment of up to I believe 6 degrees. So here you can see So here you can see the tendon duct couplers in place during match casting. As you can see, the segment on the left is a precast segment. In order to assure a good matchup, the forms for the precast segments are basically held adjacent to the existing an existing precast segment or the previous segment, and the concrete is cast against that to perform a tight seal between the two segments when they will be erected in the future. So here's just a picture of the many segments in the casting yard. And that concludes my presentation. Hopefully it gave everyone a basic understanding of balanced cantilever construction and just a very few of the issues that that must be addressed as a designer of a balanced cantilever bridge. And if there's any questions, feel free to let me know or type them into the chat pod, and I'll attempt to answer them. Thank you.
Thank you, Tony, for such an informative presentation. Just give me 1 second to switch the... Okay. One more time, thanks to Tony for such an informative presentation. I'm sure that the audience liked that and made the notes that was, important points of the segmental bridges design and construction that you brought up. We actually have a follow-up session to introduce Midas Civil, this main software that was used for analysis and design of this bridge. This session will be on next Wednesday, October 31st at 3 p.m. Eastern Time. So in this session, we will be more discuss about Midas Civil and capability of this software in terms of designing, modeling, performing analysis, and designing the post-tension segmental box girder bridges. So everybody who is keen to learn more about the benefits that Midas users are getting through the Midas Civil, please join us on October 31st at 3 p.m. As I mentioned, we'll cover an introduction to Midas Civil 2013, and we'll explain that why Midas Civil is the best software for segmental bridges. We will send you the invitation soon, so please mark your calendar for next week, October 31st. It's going to be on Wednesday. And to make it simpler for you to remember, just know that it's on Halloween Day. So if you guys want, you can join us with your Halloween costume. I hope everybody enjoyed the session and the presentation. And if you guys have any question, please feel free to send this. And I keep this session open for 5-10 minutes, and we'll turn it over to Tony in case to answer your questions. Thank you so much, and you guys have a great evening. Tony, if you would like, please just answer the questions that we get. We have so many questions, just, we can cover as many as we got time. Thank you so much. I put myself on mute and waiting for your answers.
Okay, I'll start from the first question. Was this a design build or a design bid build project?